Welcome back. In this video, we'll be looking at example 6.1.3. We're going to evaluate a definite integral with the type of square root we've been looking at. But before we do that, at the end here, I made a small mistake. So this is what I presented to you, but I forgot that the cube applied to the 4 as well. So let me erase the very end and redo it correctly. Sorry about that. All right, so I'm getting minus 16, square root of 16 minus x squared. But here I'm going to get 64 thirds, and then 4 cubed is 64 as well. All right, so let me shrink. Oh, sorry. Let me shrink this a tiny bit so I can rewrite it nicely. So I get minus 16, 16 minus x squared plus 1/3. And then I could write it as 16 minus x squared cubed plus c. So I had an extra 16 here. That wasn't supposed to be because this was cubed. All right, and this is the right answer. All right, example 6.1.3. I want to evaluate this square root with definite, this integral with definite bounds. All right, so we'll start the same way. We have 16 minus x squared again, so that means 4 sine theta dx is 4 cos theta d theta, and then my square root is 4 cos theta. My triangle will look like this with x over 4, and then 16 minus x squared as the adjacent side. And now I'm ready to rewrite the square root. So square root is 4 cos theta. The dx is 4 cos theta d theta. And so I need to integrate 16 cosine square theta d theta. All right, so far nothing's different. It's just that I started with bounds and now I need to keep the bounds alive. All right, so at this point, I have 0 and 2. I need to plug them into something. They're values of x. So my old variable is x. My new variable is theta. Let me solve for theta here. I mean, we have it as part of our method. We have it, right here. Theta is arcsine of x on A. So theta is arcsine of x on 4. And so that's what I'll use to change my bounds. So arcsine of 0 on 4, arcsine of 2 on 4. So arcsine of 0 is 0. Arcsine of 1/2, that's pi on 6. Good. All right, now I need to integrate this function. It has an even number of cosine, no sines. So I'm going to use the identities. So power reducing identity, 0 pi on 6, 16, 1 plus cosine 2 theta over 2 d theta. And so I'm getting 8 plus 8 cosine 2 theta. Now I can integrate. I know the integral of, sorry about that. I know the integral of both parts. So I get 8 theta. Remember, the variable tells you how to integrate. So if I have 8 dx, it's 8x, but if I have plus c, 8 d theta, that's 8 theta plus c, whatever your variable is. So here 8 theta, and then 8 sine of 2 theta divided by 2. I want to put plus c, but here I don't need to because I have bounds, so it's going to be from 0 to pi on 6. So I'm going to plug in pi on 6, and I'm going to subtract what I get when I plug in 0. So I get 8 pi on 6 plus, let's put 4 sine of 2 pi on 6. And then So that's at pi on 6. At 0, I get 0 plus 4 sine of 0, which is 0 as well. So I'm getting 4 pi on 3. 4 pi on 3, and then sine of pi on 3, that's root 3 on 2. So I'm getting 4 pi on 3 plus 2 root 3. All right, so the reason I did this extra example is because I want to make sure that you know the following. When applying the inverse trigonometric substitution, x equals a sine theta to a definite integral, you change the bounds using that theta is arc sine of x on a. That's the real substitution you're using. We're flipping it because it's easier, but really when we apply the bounds, when we use the bounds, we have to change them using arc sine of x over a.